Good day, everyone. This is Salazar Dixie, and we're going to report about thin layer chromatography. So, thin layer chromatography, also known as TLC, is a chromatography technique used to separate mixtures. It was discovered by M. Tissot in 1906. Thin layer chromatography is performed on a sheet of glass, plastic, or aluminum foil, which is coated with a thin layer of adsorbent material, usually silica gel, aluminum oxide, or cellulose or blotter paper. This layer of adsorbent is known as the stationary phase. So after the sample has been applied on the plate, a solvent or solvent mixture, also known as the mobile phase, is drawn up to the plate via capillary action. Because different analytes ascend the TLC plates at different rates, so separation is achieved. So on completion of separation, each component appears as spots separated vertically, so each pass has retention factor. RF is expressed as distance traveled by sample over distance traveled by solvent. So the factors affecting retardation factors are the solvent system, amount of material spotted, adsorbent, and temperature. TLC is the one of the fastest, least expensive, simplest, and easiest chromatography technique. So as you can see here, this is the TLC plate, the spot and developing solvent. So TLC has a two-phase, a stationary phase and a mobile phase. So overview. The first widespread application of partition chromatography on planar surface was paper chromatography. It was introduced in 1940s. However, paper chromatography was gradually replaced by thin layer chromatography, also known as TLC, which has become one of the most routinely used chromatography techniques. TLC is also a liquid-solid absorption technique where the mobile phase ascends the thin layer of stationary phase coated onto a backing support plate. So these are some apparatus. So the plates or the stationary phase can be prepared in the lab but are most commonly purchased. Silica gel and alumina are among the most common stationary phase, but others are available as well. Many plates incorporated a compound which fluoresces under shortwave UV. The backing of TLC plate is often composed of glass, aluminum, or plastic. Glass plates are chemically inert and best withstand reactive stains and heat, but are brittle and can be difficult to cut. Aluminum and plastic plates can be cut with scissors, but aluminum may not withstand strongly acidic or oxidizing stains, and plastic does not withstand the high heat required to develop many stains. Aluminum and plastic plates are also flexible, which may result in flaking of the stationary phase. Never under any circumstances touch the face of a TLC plate with your fingers, as contamination from skin, oils, or residues on the gloves can obscure results. Instead, always handle them by the edges or with forceps. So we have here the stationary phase. So in the stationary phase, we have silica gel G, silica gel G254, alumina, and cellulose. So the description of silica gel G, it has an average size of 15, containing a Ca 13% calcium sulfate binding agent. The application is used in wide range pharmacopoeial tests. Silica gel G254 is a silica gel added with fluorescent. So the application is, it has same application with silica gel G, where visualization is to be carried out under the UV light. And the cellulose powder of less than 30 particle size. The application is identification of tetracycline. So the preparation of TLC plate, it has the drying, storage, and handling. First, air dry, then oven. B. Controlling and marking of the layer, homogeneous in transmitted light, no unevenness and no large grains. C. The application of substance mixture for separation, no use in volatile solvents, concentration is 0.1 to 1%. Spot application by microbulb pipette, graduated micropipette, and microsyringe. The solvent or the mobile phase. Proper solvent selection is perhaps the most important aspect of TLC, and determining the best solvents may require a degree of trial and error. As with plate selection, keep in mind that the chemical properties of the analytes, a common starting solvent is 1 to 1. Hexane is to ethyl acetate. Varying the ratio can have a pronounced effect of RF. RF values range from 0 to 1, with 0 indicating the solvent polarity is very low and 1 indicating that the solvent polarity is very high. When performing the experiment, you do not want your values to be 0 or 1 because your components that you are separating have different polarities. If the value is 0, you need to increase the solvent polarity because the sample is not moving and sticking to the stationary phase. If the value is 1, you need to decrease the solvent polarity because the compound was not able to separate. So one component of a mixture is insoluble in given solvent, but another component is freely soluble in it. It often gives good separation how fast the compounds travel up. The plates depend on two things. If the compound is soluble in the solvent, it will travel further up to the TLC plate. How well the compound likes the stationary phase. If the compound likes the stationary phase, it will stick to it, which will cause it to not move very far on chromatogram. It should be able to determine which by looking at the RF values. Acid and bases, polar compounds, often produce streaks rather than spot in neutral solvents. Streaks make it difficult to calculate an RF and may occlude other spots. Adding a few percent of acetic or formic acid to the solvent can correct streaking with acid. Similarly, for bases, adding a few percent of triethylamine can improve results. For polar compounds, adding a few percent methanol can also improve results. The volatility of solvents should also be considered when chemical stains are to be used. Any solvent left on the plate may react with the stains and concealed spots. Many solvents can be removed by allowing them to sit on the bench for a few minutes, but very non-volatile solvents may require time in vacuum chamber. Volatile solvents should only be used once. If the mobile phase is used repeatedly, results will not be consistent or reproducible. So this is the mobile phase. We have the TLC chamber, the TLC plate, the spotting line. So the component of mobile phase, we have methanol is to chloroform and to acetic acid, has a ratio of 8, 10, and 0.2, and has a RF of 0.8. Methanol, chloroform, and acetic acid, which has 3, 7, and 2 drops, has an RF of 0.85. The chloromethane, to methanol and acetic acid, 4, 1, 2 drops, has 0.86. The chloromethane to methanol, 2 to 3, has 0.78. The chloromethane and methanol, 4 to 1 is 0.78. The chloromethane is 1, has 0.88. Chloroform has 1 ratio, and the RF is 0.30. Chloroform and methanol has 9.9, and 0.1 has an RF of 0.5.
So to continue about our topic, I'm going to be talking about pipettes. So spots are applied to the plate using very thin glass pipettes. The capillary should be thin enough to apply a neat spot, but not so thin as to prevent the uptake of an adequate quantity of analyte. Here is a popular method of producing thin layer chromatography pipettes. Heat a glass capillary in the very tip of a Bunsen burner flame just until it becomes pliable, and then pull the ends apart until the center of the capillary is significantly narrower. Snap this in half and use the thin end to apply spots. Spotting and developing. Developing a TLC plate requires a developing chamber or vessel. This can be as simple as a wide-mouthed jar, but more specialized pieces of glassware to accommodate large plates are available. The chamber should contain enough solvent to just cover the bottom. It should also contain a piece of filter paper or other absorbent material to saturate the atmosphere with solvent vapors. Finally, it should have a lid or a cover or other covering to minimize evaporation. Cut the plate to the correct size and using a pencil. Never use any pen. Gently draw a straight line across the plate approximately 1 centimeters from the bottom. Do not use excessive forces when writing on a TLC plate, as this will remove the stationary phase. It is important to use a pencil rather than a pen because inks commonly travel up the plate with a solvent. An example of how black ink separates is shown in the selection labeled examples. Using TLC pipettes, apply spots of analyte to the line. Make sure enough sample is spotted on the plate. This can be done by using the shortwave UV light. A purple spot should be seen if the spot is not visible. More sample needs to be applied to the plate if a standard of target compound is available. It is good practice to produce a cool spot by spotting the standard onto a spot of the unknown mixture. This ensures the identity of the target compound. Next is place the plate into the chamber as evenly possible and lean it against the side. Never allow the book solvent to rise above the line you draw. Allow capillary action to draw the solvent up the plate until it's approximately 1 centimeter from the end. Never allow the solvent to migrate all the way to the end of the plate. Remove the plate and immediately draw a pencil line across the solvent front. Use a shortwave UV light and circle the components shown with a pencil. So this is the sequence in thin layer chromatography. If fluorescent plates are used, a number of compounds can be seen by illuminating the plate with shortwave UV. Quenching causes dark spots on the surface of the plate. These dark patches should be circled with a pencil. For compounds which are not UV active, a number of chemical stains can be used. These can be very general or they can be specific for a particular molecule or functional group. Iodine is among the most common stains. Plates are placed in a jar containing iodine crystals or covered in a silica gel with iodine dispersed throughout for approximately 1 minute. Most organic compounds will be temporarily stained brown. Some popular general use stains are permanganate or decam or ceric ammonium molybdate and p-anisaldehyde. These can keep in jars which plates are dipped into or spray bottles. To develop with a permanganate, spray or dip the plate and heat it with a heat gun. Hold the plate face up 10 to 20 centimeters above the heat gun until the book water evaporates. Then move the plate to 5 to 10 centimeters above the heat gun and heat it until white, yellow, or brown spots appears. Overheating will turn the entire plate brown, obscuring spots if possible. Plates are used. It is often easier to see spots through the backing because it is harder to overheat. CM or CAM and P anisaldehyde stained plates are developed similarly. Overheating CAM stained plates turn everything blue. Thin layer chromatography principle. Like other chromatographic techniques, thin layer chromatography or TLC depends on the separation principle. The separation relies on the relative affinity of compounds towards both phases. The compounds in the mobile phase move over the surface of the stationary phase. The movement occurs in such a way that the compounds which have higher affinity to stationary phase move slowly while the other compounds travel fast. Therefore, the separation of the mixture is attained. On completion of the separation process, the individual components from the mixture appear as spots as respective levels on the plates. Their character and nature are identified by suitable detection techniques. So various applications of thin layer chromatography or TLC are as follows. Purity of any sample. Purity of sample can be carried out with TLC. The comparison is done between the sample and the standard or authentic sample. If any impurity is detected, then it shows extra spots, and this can be detected easily. Identification of compounds. Thin layer chromatography can be employed in purification, isolation, and identification of natural products like volatile oil or essential oil, fixed oil, waxes, alkaloids, glycosides, and steroids, and others. Examination of reaction. Reaction mixture can be examined by thin layer chromatography to assess whether the reaction is complete or not. This method is also used in checking or other separational process and purification processes like distillation, molecular distillation, etc. Biochemical analysis. Thin layer chromatography is extremely useful in isolation or separation of biochemical metabolites or constituent from its body fluids, blood plasma, serum, and urine, and etc. So in chemistry, thin layer chromatography methodology is increasingly used in chemistry for separation and identification of compounds which are closely related to each other. It is also used for identification of cations and anions in organic chemistry. In pharmaceutical industry, various pharmacopoeias have adopted TLC technique for detection of impurity in pharmacopoeial chemicals. So various medicines like hypnotics, sedatives, anticonvulsant, tranquilizers, antiemetics, analgesic, local anesthetics, steroids have been tested qualitatively by TLC method. One of the most important applications of thin layer chromatography is separation of multi-component pharmaceutical formulation. In food and cosmetic industry, TLC is used for separation and identification of colors, preservatives, sweetening agents, and other various cosmetic products. So attached here is the link in YouTube. You might want to check it out if you want to know how thin layer chromatography being performed in the lab. So here are references. And that would be all. Thank you.